All right, let's dive into one of my favorite ideas in all of computer science, universal hashing. It sounds complicated, but it's this really beautiful, clever trick that makes so much of our digital world just work. It's the secret sauce that lets computers operate at mind-boggling speeds. So, let's pull back the curtain and see how it's done.
I mean, have you ever really stopped to think about that? You type something into Google, or you search for a file on your laptop, and bam, the result is there, instantly. How on earth is that possible when you're searching through literally trillions of pieces of data? It feels like actual magic, but it's really just an incredibly elegant solution to a classic problem.
And that problem has a name. In the world of computer science, we call it the dictionary problem. It's all about how you manage a gigantic collection of stuff and can still find, add, or get rid of any single item in the blink of an eye.
So, here's the core idea. You've got this enormous, practically infinite universe of possible things. Think every username that could ever be created. But at any given time, you only really care about a much, much smaller group, the usernames that people have actually registered. And on that smaller group, you need to do three basic things, right? Add a new one, delete an old one, and find a specific one. And you have to do all of it fast, like really fast.
Now, you might think, okay, let's just use a simple list. Well, that's great for saving space, but to find anything, you might have to look through every single item. We call that O of n time, and it's just way too slow. The other extreme is something called a bit vector. It's incredibly fast, what we call O of 1 or constant time, but it needs a dedicated slot for every possible item in the entire universe. That would take up an insane, impossible amount of memory. So we're caught in this classic trap, this trade-off between speed and space. And this is where a really smart idea called hashing comes into play. The goal of hashing is to try and give us the best of both worlds, the lightning-fast lookup of the bit vector, but with the small memory footprint of a list.
The way it works seems almost too simple to be true. You take your item, you feed it into a special function, a hash function, and it instantly spits out a number. That number is the exact address, the exact slot in an array where your item lives. It's like having a librarian who can just glance at a book's title and instantly point to the exact shelf where it belongs. No searching needed.
But of course, there's a catch. What if the hash function tells you to put two different books on the exact same shelf? That's called a collision. The classic way to deal with this is something called chaining. Basically, each slot in our array isn't just a single spot anymore, it's the beginning of a small list. So if multiple things hash to the same spot, no big deal. We just add them to the list at that location. And when it works, oh man, it works beautifully. Look at this. In a good case, our hash function spreads all the numbers out really nicely across the different slots. The lists or the chains are all super short, so finding anything is still incredibly fast. This is the dream.
But what happens when that dream turns into a total nightmare? See, this simple hashing approach has a fatal flaw, a real Achilles heel that can bring the entire system to its knees.
And here is the fundamental killer problem. If your hash function is fixed, if it's predictable, then a clever attacker, or even just a string of bad luck, can create a set of data that's perfectly designed to cause collisions over and over again. This isn't just a theoretical worry, by the way. This can be weaponized in denial-of-service attacks to intentionally cripple a website.
And this is what that disaster looks like. We're using the exact same hash function as before, but with this new set of data, every single item hashes to the same spot, slot 0. Our beautiful, efficient hash table has just collapsed into one long, miserable linked list. All the other slots are just sitting there, completely empty.
At this point, our search time is right back to being O of n. We're no better off than that simple, slow list we were trying to avoid in the first place. The whole point of hashing, all that cleverness, is gone, wiped out, all because our system was predictable. So, how do you fight a predictable attack? You become unpredictable. And this is where randomness enters the story, not as a source of problems, but as our hero. It is such an elegant and powerful solution. So think about it like this. Instead of having just one librarian who always uses the same system, what if we had a whole team of librarians, a whole family of them, and every morning we pick one of them completely at random to be in charge for the day? An attacker might figure out how to trick one of them, but they have no way of knowing which librarian is on duty today.
And this is the big idea, formalized by Carter and Wegman back in 1977. It's called universal hashing. We don't just use one hash function, we create a big family of them. And the magic is this. If we pick one function from that family at random, we get a mathematical guarantee that for any two items you could possibly choose, the chance that they collide is ridiculously small.
And building one of these families isn't some crazy abstract thing. It's actually pretty practical. Here's a classic recipe for it. First, you grab a big prime number. Primes are great at scrambling things up and spreading data out evenly. Then, and this is the secret sauce, you pick two numbers, A and B, completely at random. Those two random numbers define your specific hash function for the day. Every time you start up, you pick a new A and B, and you get a brand new, unpredictable hash function that no attacker can guess.
So what do we get for all this cleverness? What is the ultimate reward for embracing randomness? Well, it's a performance guarantee that is just, it's the holy grail.
This is it. O1, constant time. What that really means is that, on average, the time it takes to do anything, search, insert, delete, stays the same. It doesn't matter if you have 1,000 items in your table or 1,000,000,000,000. The operation takes a tiny, constant amount of time. It doesn't get slower as you add more data.
So how is that even possible? Well, here's the beautiful part. Because our function is chosen randomly, nobody, not an attacker, not bad luck, can force a bunch of items into the same slot. The math proves that the expected or the average length of any chain in the table will be less than 2. That's just wild. And searching a list with, on average, less than 2 items, that's basically instant.
So let's just put it all side by side. A linked list is efficient on space, but way too slow. Other smart data structures like balanced search trees are a big improvement, giving us logarithmic time, but they still get a little slower as the data grows. But then you have universal hashing. It hits the absolute jackpot. Efficient ON space. And that incredible O1 expected time. It is the undisputed champion for the dictionary problem.
So let's just recap the journey we took. We started with a problem. Any fixed, predictable system can be broken. We found a solution. Fight predictability with randomness. We did that by not picking a random number, but by picking a random algorithm from a carefully designed family. And the result? Universal hashing, which gives us that perfect combination of efficient space and constant time operations. And that kind of leaves us with this really big, fascinating question. This idea of using randomization to make algorithms robust against the worst-case scenario is just so powerful. It's a cornerstone of modern cryptography, of network design, of so many fields. It really makes you wonder, where else can a little bit of strategic, deliberate unpredictability make all of our complex systems fundamentally stronger and safer?